Hard to believe. I find it takes a long time, then the last couple of weeks just fly by. But we're here on April 11th. We're going to finish up the standard template library and files and streams. Probably be a little bit of a short class today. After that, we will, I'll do a brief review, although there's a couple hints, but it's not a very long review. You can take notes if you want. I guess practice final acts as your review material. So I won't really be giving you any more review material. Although I do encourage you to sort of organize your, study your topics and the things you need to study yourself. But yeah, let's see. Tutorial 10 is due on Wednesday. If you have any outstanding tutorials you want me to mark, please let me know, either on Discord or by email. But yeah, any questions on the schedule? Okay. All right, so last class we were talking about the standard template library. Where were we? Not here. Here. So we were talking about example P6, where we were using a list, from the standard template library, the list class, which is a templated class. Well, let's take a quick look at it, I guess. So it's here. We made a bunch of student objects. And then, we use the output stream iterator on cout. We pushed these objects onto our list, and then we did a little bit of, we called the sort function on the list, which works for the list function, not so much for vector and others. So this is not part of the algorithms library. This is something that the list class lets you do. And then we copied it out. So if you just call sort on a regular, on just the student object, what happens is it sorts according to this overloaded less than operator. If you've not overloaded the less than operator, then that code will not compile. So if you want to sort, you probably either want this, or you can supply some custom function, right? So we sorted here using the less than operator, and we sorted here by passing in a function that returns a Boolean and takes 2 students as arguments, right? So that is, as long as it has this function signature, then you can do whatever you want in here. And we made it a friend of that class to make sure that it worked. So yeah, so that's sorting on a list, and we are going to later see how to sort on a vector. So yeah, that's just a review. Copying our own objects works as long as we have the stream insertion up. I'm not sure what I meant there. This does not make any sense to me whatsoever, but this is valid. It's not that only if you have the comparison less than operator overloaded, but if you by default, that's where it's going to go. All right, so the next thing we're going to look at is decks. So these are double-ended queues. And what that means, so we've implemented a queue, right? Which a queue was very fast at removing something from the front of the list or adding it to the back of the list. So those 2 operations were quick and efficient. A double-ended queue, we can do both. If I want to add to the front, that happens fast, and I don't need to make copies of my elements. I could add to the back, that also happens fast, and I can remove from either the front or the back very quickly. So, and the nice thing about the double-ended queue, so you could take a linked list class and implement a queue quite easily. The double-ended queue is actually could be a linked list, but it's not. It's actually something a little more complex. I did look it up a little bit, but it seemed a deeper dive than I really wanted to get into at the moment. The nice thing about it is that even though you can add to the front and the back really quickly, the same as you could do with a doubly linked list, you also get these random access iterators. So it is actually a pretty good data structure if you're looking to be efficient. Grows as needed, supports random access, does not make copies of your objects. These are all very good things. Of course, if you insert it the middle, so you can insert it at either end really quick. There's an insert, if I try and insert something in the middle, then there might be some copying that happens. But all right, just to, and deck is not the only other collection class, but we'll show you this, and then you can, if you need other collection classes, you can research them on your own. So we have our student class again. We've overloaded the less than operator and the double equals operator. And otherwise, it's just the same old entity object that we've been using up till now. So we make a bunch of students. We have an output stream iterator, and then let me see what we're supposed to do here. All right, so I'm going to declare a deck of students. I've included the deck library. So yeah, a deck again is the templated library. So we will, sorry, not string, but student. Studec. And then we will push a bunch of students onto the back of studec. So I'll push Matilda, Amy, Stanley, and Joe. So these 4 students. We'll save Bob and Alice and Ted for later. And then we can say, print it out just as a, sanity check. Make sure that everything's working. And I can use, of course, the copy command, studec.begin. So we take the iterator that marks the beginning of the data structure, the iterator that marks the end of the data structure, and then the output iterator. So we're going to copy all of those to the output iterator. So that's essentially as if I looped over everything in my deck and fed it into the stream insertion operator. All right, and then cout. Okay, P7 CD. Okay, so our deck of students, Amy, Matilda, Amy, Stanley, Joe, that's fine. Let's just, let's make sure that we are recording when we're making a copy. Yeah, that should be fine. All right. So when we push our students onto the deck, of course, copies are made because we're storing objects. So every time we store objects, we copy them into the data structure, right? If we stored pointers, then we copy the pointer in, but the original object stays, wherever it is. We don't make copies of that. But you could see, if we had added these students to the vector class, then we would have made a whole bunch of copies as the vector grew and doubled in size every time. All right. So now we can say, here, let's bring in the vector class. Maybe we want to compare these two a little more closely at the end. Okay, so I've pushed on the back. No copies were made except for the first original copy. That's great. Here I'm going to say pushing students to the front. Now you can't really do that with a vector. Well, you can if you use iterators, right? So you can insert at the front of a vector using iterators, and then we would see a bunch of students being copied. But for the deck, we have a push front function. So oops, push front. And we can do Bob, Alice, and Ted, I guess it was. Okay, and then I can print those out. Okay, so the point is that, and we're printing out every time we call the copy constructor, so we'll see that we can actually add to the front of the deck quite efficiently without a whole bunch of extra copies being made. Okay, so we made one copy of each student that we pushed on the back. We printed them out, and then we made one copy of each student that we pushed to the front, and then we printed them all out again. So in each case, only one copy is made. As the deck grows and shrinks, students are not copied all over the place. So it's actually quite efficient. Yeah, questions so far? Okay. The other nice thing is we get random access. So I could actually, yeah, sure, let's do that. studec.size. We could do this the old-fashioned way, studec. All right, so we can print out our deck of students the old-fashioned way using random access. So it does sort of combine the best of both worlds of your vector and your list class. The other thing is, because we have random access, we actually have random access iterators as well. So yeah, we can declare an iterator. I can say it equals studec.begin. So I'm going to grab the iterator that points to the first element of my studec, and then I could say print out the student at position 3 using random access and with my iterator. So the student at position 3 is Bob, the chemistry major, which is what we have here. So yeah, 2, being the third student in our student deck. Okay, questions on that? All right, let me see here. Let's compare and contrast to the vector. If I can do. Okay, so I can push some students onto the back of the vector. Let me actually get rid of this for now. I push some student on the back of the vector, print them out, and then push to the front of the vector using the insert, right? So we're using the, insert takes an iterator as an argument. So the iterator is the location and then the student. So we have yeah, so we push some students onto the back, Matilda, Amy, Matilda. Of course, we have a bunch of copies being made. Then we pushed 3 students. We inserted 3 students onto the front of the vector. And again, we had a bunch of copies being made. So as this vector expands and the students get pushed back, Matilda, Amy. Oh, yeah, I put the wrong thing here. That's why. Okay, my vector of students is Matilda, Amy, Stanley, and Joe. And then, yeah, when I insert Bob, Matilda, Amy, Stanley, and Joe all have to be copied over. And then Alice. So yeah, I don't know. It looks like the Alice and Ted. Well, I'm not sure exactly what's happening there. It looks like there's either maybe some constructor optimization, or maybe it implements the insert a little bit differently than I expected. It seems like maybe, so I was under the impression this was the same as the array list, but it looks like maybe they do something a little bit different here. Anyway, all that to say is if you insert at the front of the vector, copies are going to be made, so it's not that efficient at it. All right, questions on that? Alrighty. So we'll talk about associative containers. We're not going to get into them, but associative containers are containers that use keys. So the keys are stored in some user specified order. The default is ascending. And of course, this means that the less than operator should be overloaded for your class if you're storing your class. Or we can supply our own function, a predicate. The types of associative containers are set, multi-set, map, and multi-map. So yeah. So a set is storing the keys only, right? So we saw before how we had a key value pair with map item when we were taking templates. So a map item is basically 2 things, right? 2 values. One is used as the key and one is used as the value. However, in a set, you basically only store the keys. And you may think, well, how useful is that? It can be useful. At any rate, a set, we store the keys only, and we do not allow duplicates. Multi-set, we get to store the keys, but we do allow duplicates. A map is a set of key value pairs. The regular map has no duplicates, whereas the multi-map, we have key value pairs, and yes, there is duplicates. And when we say duplicates, we mean the keys, right? So here the keys cannot be duplicated, and here the keys can be duplicated. We can duplicate the values, that's not a problem. All right, so we get functions like insert, find, lower bound, upper bound. So set and multi-set might be implemented using a hash table or a hash map, right? So hashing is actually quite extensively used in computer science, although we haven't touched on it here. The iterators we get for these associative containers are bidirectional. So yeah. But we're not going to do any examples here. Any questions though? All right. Container adapters, we've actually written a couple of container adapters. Well, we wrote one for stack, right? So we took a vector and we adapted it into a stack. And all that means is that we stripped away some of the functions, right? So vector can be made to be used as a stack, but we wanted to hide the functions that we didn't want the users to have access to. So that's the similar idea behind these container adapters. I can take a container, I can implement a stack using a vector or a list. Queue is also a list or something else, I forget, maybe a deck. So I can specify the underlying type of container. And then priority queue, which is if you've done min heaps and max heaps and things like that. So we put things in into our data structure, and then there's a priority associated with it. So the things with the, in some sense, greatest priority, I guess, are the things that come off the priority queue first. So yeah, a stack can be implemented with any sequence container. A queue can be implemented with a deck or a list, a priority queue with a vector or a deck. We specify the underlying containers when we say, right, so maybe we say a stack of strings, and then we can specify a vector. And I think we have to specify string here as well. So that's how we would specify a stack, and a stack using a vector in this case. They do not support iterators. So you get only the functions that come with it, right? So you can't run algorithms on them, at least not from the algorithm library. All right, questions on that? Okay, so algorithms are global function templates that operate on containers, mostly using iterators, right? So we're going to include the algorithms library, and then we'll have a bunch of global functions that we can use. So yeah, of course, the types of algorithms we can run depends on the types of iterators we have. We can't, for instance, sort an output stream. That doesn't make any sense. But yeah. So algorithms often use a pair of iterators, often return an iterator. And yeah, as mentioned, algorithms require iterators with specific properties. So examples of algorithms are sort, copy, remove, fill. We'll see a couple right now that most likely would be useful on tutorial 10. Okay, so again, we have our student with the less than, the equals, the output stream. It's not const, but we'll ignore that for now. So we're going to use our vector, since that is sort of the all-purpose. And we saw earlier how we couldn't sort on a vector, right? Stuvec.sort does nothing. There is no sort function. But what we can do is include the algorithm library. And then if we want to sort our student vectors, well, first of all, let's print them out as a, what a mess here. Okay, so we have our output stream iterator, and then we can print out our, oh, do I not? I have to include my iterator. All right, so now we have an output stream iterator. We didn't sort them yet. So a vector of students, we'll just print them out. Oh, what did I do? Yes, that does need to be const. Oh, it seems I don't have an that was actually the problem. I had an extra function that I did not need at the moment. Okay, one last thing. We do not need to see how many copies are being made or what's being destroyed. Okay. I have a destructor here. Yes. Okay, so there's my vector of students, and now I can call sort using my algorithm library. So I can say it's a global function, so I just call it. I supply my, what do we call it, studvect. The beginning of the items I want sorted, the end of the items I want sorted. So yeah, that's it. Nothing too complicated. I pass in the beginning and the end, and then I can print them out. Sorted using the overloaded operator. Which I believe is alphabetical. So yeah, Amy, Joe, Matilda, Stanley. Yeah, Amy and Matilda switched spots. So yeah, not too different from what we did with the list, except now we're using iterators as a go-between between our algorithms and our vector. Questions? Easy stuff. All right, so I'm going to what am I going to do here? Yeah, let's do this. So I'm going to include a static function in my student class. Let's say I wanted to sort according to GPA. So I want the highest GPAs. Well, I can recall this sort function, but I could pass in the same as with the list, where we could put in our custom sort functions. We can here as well, as long as it has the correct signature. So we're going to pass in student comp. So now we're sorting by GPA. Yeah, not, I mean, they're almost still in the same order, but there has been a couple of swaps. So yeah, we can sort by the GPA, passing in our custom sort function. All right, what else? I'm gonna copy. So this, we can check if all of the students are passing. So we can use this all of function that's going to iterate over all of these students and check to see if they pass. This is a global function that we will say if your GPA is over 6.0, then you pass, right? So we'll declare it here. We need to make it a friend. Never mind. Let's put that here. Okay, so now in my main, this has to have a. All right, so we could check to see if everyone is passing. So it's going to go through the entire vector and call this pass function on each of the students, right? And if they all are passing, then it'll say everyone passes. It says not everyone is passing. So if we look at, of course, the GPAs, we can see that Stanley here is not passing. So we could just look at the first three students. Since this is a random access iterator, we can use this, we can use pointer arithmetic in some sense. So we can say, well, let's check if all of the students up until Stanley are passing. And then it says everyone is passing. Right. So yeah, just another function that you can use from the algorithms library. So if you look at the C++ reference, basically if you type in C++ algorithms library, it'll bring you to this page. And it gives you all of the possible functions that you can use from this library and a little bit on how to use them. Yeah, I guess. Oh, I guess one more relevant thing that that we should look at is let's find all of the passing students and put them into any of it's very similar. Let's find all of the passing students and put them into a new vector. So we're going to say let's get rid of all this extra noise. So we have our student vector, studvect. We pushed 4 students on. Now we're going to make a copy of all of the passing students from studvect. So we're going to declare a new vector called vector2 that has, to begin with, the size of studvect, right? So we're going to initialize it so that there's room to copy these students into this vector. And then we're going to say, we want to declare, let's copy it over. Okay, so we'll declare a vector iterator. We'll say copy if, and then this has to be student. So this iterator is going to keep track of where we ended up, where is the last element that we copied. All right, so it's going to become important, but this will copy all of the passing students from studvect.begin to studvect.end into studvect2.begin. So then what we can do at that point is print out all of the students in studvect2. Okay, so we copied all the passing students in. So we initialized the vector studvect2 with the size of studvect, which was 4. So what happens is that 4 of these default students were created. Then we copied all of the students from studvect that were passing into studvect2, which was Matilda, Amy, and Joe. Stanley did not get copied, so this one is left to be Hey You. So that's maybe what we want, maybe not. What we can do is we can resize student vector. So I only want the size of all of the students that I copied. So what I'm going to say is I'm going to use this distance function. Studvect2.begin. The iterator is pointing to studvect2 as well, right? So we assigned it here. This actually returned the last element that was copied into studvect2. Sorry, this is a distance function. So we want the distance between studvect2.begin and the iterator. And yeah, that's it. So this should give us the proper size of 3. And then when we print out our vector, we only get the 3 students that we copied. So yeah, this is a little bit of a slightly complicated set of function calls just to copy all of the students that passed from one vector to another First, you initialize the vector with the appropriate size here. Then you declare an iterator. You call the copy function. The iterator that's returned points to stuvect2, the last element of stuvect2 that was copied. Then we can resize stuvect2 according to the distance between the beginning and wherever this last copy was. And then we're good to go. But yeah, a lot of work just to copy a bunch of stuff over. But questions on that? Maybe we won't be done early. All right. Okay, there's a whole bunch of other stuff that you can do, but I think you get the idea behind the algorithms. So yeah, iterators, you declare functions if you want things like, you know, to check if the students pass or not, or to compare two students, and then yeah, you can call the algorithms. Okay, so that brings us to the end of the STL. Yeah. So the next thing we're going to look at is actually sort of similar, files and streams. This is relatively short, but there is a couple neat things we can do with it. All right, so in this section, we'll look at streams in general. Then we'll look at files. Basically, we can use files as a stream, right? It's just a sequence of bytes like any other data stream. And then we'll talk a little bit about error state flags. All right, so a stream is thought of as a sequence of bytes. So data going from source to sink, right? Often we buffer it. We don't really need to write everything to the file right away. We store it in memory somewhere, and then when enough of it is accumulated, then we can write it to the file. We can go from a source to a program, so from a file or from the internet to our program, or we can go from program to source, so we can write from our program to a file or to the internet. Data source and sink examples. So the keyboard would be a source, the console would be a sink, files could be sinks or sources, a printer is a data sink, network adapters, sink and source. So the input output stream library has, it has some generic input output templates. So we can actually use streams on different types, right? So the input streams library has the important object is the cin. The output stream library, the important objects cout, cerror, which we did not use a lot, and clog. So this by default prints to the screen, but you can have it print somewhere else, and clog, I believe you can specify a file for that, although I would have to look that up again. So each stream maintains some error bits. So we have a good, we have a bad bit, and a fail bit. And then there are member functions we can use to test the error bits. And there's different things that can happen that flip these bits. We also get the overloaded not operator. So what that means is that we can test a stream directly, right? We can do things like returns true if one of the error bits are true. So I could say if, not cin. Right, so that means if the stream has gone bad, then we will do something. Or we can have this cast to the void pointer operator. So this sounds really complicated, but what that means is that we can simply pass in our stream. And it will return true or false, basically. True if it's still in a good state, false otherwise. All right, so let's take a look at streams and some of the ways that this can all go wrong. That would be okay. So we have our main, we have a max buffer preprocessor constant. We've declared 4 different functions that we're going to do, we're going to do some, we're going to run and see what happens. So the first thing we're going to test is the extraction operator. So the extraction operator, we will take in 2 strings, we will declare 2 strings and a number, and then we ask for 2 strings and a number, right? So the user will then put them in and we can test this stream directly. So recall that these stream extraction operators are set up for cascading. So they return a cin object. So this whole thing, this whole expression returns a cin object, and then that cin object is tested using the cast to void, which returns true if it's still in a good state and false otherwise. So what we do is we just keep printing it out until something goes wrong, and then we exit. When we exit, we can check to see if our stream is still good. And if it is, we print out all is well, and if otherwise we print out something went wrong. We need 20, eh? Okay, so testing stream extraction operator, enter string number. So hi there 3. So you said hi there 3, excellent. 1, 2, 3. You said 1, 2, 3. So integers are strings, that's not a problem. But if I said A, B, C, something went wrong. So at that point, this returned false. And then it returned false because this bit was flipped. So we got some bad input. All right, so that's, one way to use the stream extraction operator. All right, questions? Yeah, easy peasy. End of file. So there's, yeah. So we can also use a end of file operator. We can check the end of file flag. So what happens is that we can trip the end of file by using Control D if we're inputting from the keyboard. Otherwise, of course, it can get written to your file and then read in from your file. So if we wanted to instead of ending on a bad bit, we can check to see if we've reached the end of file. So we'll take a string, we'll read it as input, and then while we haven't reached the end of file, we're going to output those strings. And then when we're done, we'll say all done. Hi, you said hi, hi there. You said hi, you said there. 1, 2, 3. You said 1, you said 2, you said 3. So then I do Control D, and it says all done. So Control D, end of file. You can read it in from the. I guess it not only does it end the file, it ends the console. All right. Good questions, I think. I mean, if you have questions, just speak up. I think this is pretty straightforward so far. There are other ways to get, actually, let's do get line first. Let's do get. So there is a get for the cin. That's right here. So I can read in a character at a time. So I have this cin.get that returns whatever the character is. And so I can do sort of a more low level way of getting input. I read in a single character at a time until I reach a new line character. So until the user presses enter, I keep reading in this character and adding it to my string. Okay, so then So testing the get, hi there, how are you? Enter, you said, hi there, how are you? And, you know, although it seemed pretty seamless, we were reading in one character at a time. All right. Questions? No. All right, our getLine function. Sorry, 1 second. I don't want to. All right, so let's say I wanted to, enter a string terminated by enter. I can use getLine. And so I've declared with getLine now, instead of a string, I have to declare a character array. So this is statically allocated using, you know, so it's an array of 80 characters. So if I go over, I'm guessing I'll get a seg fault, although I'd have to test it. But I can call cin.getLine. So I can read in a bunch of characters at once into my character array. And I'll say I read at most this many. And then, I can say, you said this. So enter a string terminated by enter. So hi there, how are you? You said hi there, how are you? All right. So by default, we terminate by enter. So yeah, if I did, yeah, well, but I can, of course, I can make another character be my terminator, which means that I'm going to take this and say, well, terminate when you reach this character, the star. Now, it's still going to let me type until I press enter, but then we'll see that it only takes up to the star. Oh yeah, blah, blah, blah. So enter a string terminated by the star. So hi there, star, how are you? But it only goes up to hi there. Okay, so those are basic ways we can take input from the console. Questions? All right. Okay, so we basically have two different ways to input from the stream or extract things from the stream. So if we know what kind of data we need, so we can read things in directly to an int or a float or something like that using the stream insertion or extraction operator. Yes. Of course, we need to know what type of data we're receiving. For unformatted data, we can use get or getLine, these read-in characters. So basically any character will get accepted. The end of file marker is OS independent. So calling on this will be a reliable way to determine if you've ended your input or not. Okay, so files. We can think of as a file as a type of stream that's kept in persistent storage, also called non-volatile storage, which means that basically it lasts, or it should last. So a file is an array of bytes terminated by an end of file marker. And in C++, we can represent these files as objects. So yeah, the inheritance hierarchy or the class hierarchy is this. I have input streams. I have output streams. My input output stream inherits from both of those libraries. And then I have an input file stream that is a derived class from input stream, and an output file stream that's a derived class from output stream. And then I just have file stream, which combines them both. So yeah, input file stream represents the input files. Output file stream represents the output files. Both maintain a file buffer object. When this object is destroyed, the destructor is called, which closes the file, writes the buffer and closes the file for us. Since they're streams, we can use the not and the cast to void operators. We can just test them directly. Useful member functions, we can call open or close. The constructor can optionally open the file. Second argument is the mode. And in input files, we can reposition the pointer. So there's lots of, fine tuning we can do, but we will look at some very simple examples here. Okay, so let's say we had, so we're including our student object. Again, it's the same old student object we've been seeing for a while. But what we're going to do is we're going to read in students.txt. Are we going to do that? I don't think so. Let's read out a file first, and then we can read it in. I don't think we have a student. Okay, so same idea, except we're going to write students to a file. So we'll say a student consists of a number, a name, and a major program, and a GPA. We will open this file, students.txt, just by, so this is a output file stream object that takes as an argument the name of the file. We check to make sure that it was opened correctly. If something went wrong, this would return true. And then we are going to take input from the user and print it to the file. So we can say while cin, so it's a number, name, major program, and GPA. So those are the 4 things we need for our student, and then we can spell that correctly. Then we have a couple options. We can say, but for the first option, we'll do things simply. So we'll say output file. We use these stream insertion operators, and I'm just going to write all of these things separated by spaces and followed by the end line. Okay, so and this will continue until I basically type in something that's that it doesn't accept. Okay. All right, so let's take a look at oops. Okay, so P2 out, enter student number, name, 2, 3, 4, 5, 6, Bob, comp sci, and the GPA. Bob's pretty smart. Mary, math, 11.0. Cindy's in history, 10.0. And then I can control D and file that. And if we look here, we see that there's a students.txt, and I see Bob, comp sci 12, Mary, math 11, Cindy, history 10. All right, so we've written our students out to the output file. Now in our input file, if we want to read these in again, we can go to, not here, in.cc. Yeah, so we make an input file in file.txt. So student.txt. So by default, this is going to be read. You can declare a file that is both read and write using, what is it, iOS something, some flag. Read, write. It's some acronym that I can't remember. But for now, we're just going to use the simplest version of this, the input file. So if we open this file and something goes wrong, we of course exit. But what we're going to do is read in the students and push them into a vector. So we'll say while in file, and we'll use the stream extraction operator now and say number, name, major program, GPA. Okay, so if all of those are read in successfully, then we will make a student and push that onto the vector. Right, so we'll make a student using number, name, major program, GPA, push it onto the vector. And then at the end, we can print it out. Okay. Oh, I don't want to do that. Did I just overwrite that? Let me see. Yep. All right. So let me print that in again. Yeah, and you can see them as they're being written. Okay, so now we have our file that we can read from. So we read in the students and then we make new student objects on our vector and print them out. And now we have this. How do we read different formats of files, say CSV? You can, that's a good question. Let me think. I would have to look up how to, yeah, you're right. So comma, so you could use an iterator, of course, but there might be a way to set the delimiter in the output stream. But yeah, I would honestly have to look that up right now. I can't remember off the top of my head. But yeah, that's a very good question. So how would we read this if this was a comma separated value? Maybe I'll look it up at the end of class. For now, we'll stick with spaces. So yeah, maybe it's not that. Let me see here. Changing the delimiter. All right. It looks a little complicated for, I mean, it's not that complicated, but it's complicated considering our time frame. So I'll just, there is a way to do it if you, yeah, something like this. Imbue. I don't know. I would have to read it in detail. Sorry. I could end up using it wrong. But yeah, so there is a way to do it. I don't know off the top of my head. Okay, other questions? All right. So the other interesting thing you can do is, well, you see in the student class, we've overloaded the stream insertion operator. So what I can do here is say, instead of printing all of this to my out file, this stream insertion operator works for my files as well. So I can say out file, I'll make a student object, num name major GPA, followed by an end line. So yeah, this will just print it out in the same format that I used. So let's see here. So that's currently what it looks like. P2 output now. So enter number, name, so 100, 1, 2, 3, 4, 5, 6. Bob is the first student ever. Comp sci 10.5. Oh, oops. Well, there's a comma in there, but that'll have to do. So Bob's name's with a comma, but we can see when it printed it out using the format that we specified. So now we have this student and the GPA. And I could say 100222333, Mary, math 12.0, 100444444, Alice, history. Oh, I keep putting in the commas. 9.0. All right, so, and then technically we could read these back in, but of course this presents a problem because we have these extra strings here, this GPA and this student string. So our input file, we could read it in by having an extra string called garbage. So when we read it in, it's going to say, the first thing we read will be garbage. And then, so that accounts for this string here. So this will read this in and throw it away. And then we also want to read this GPA, which is just before the GPA. So we'll read in garbage here as well. And then we'll just toss that away. Okay. All right. So for some reason that stopped working. Okay, so we still read in our students. Now we just had to toss away the extra formatting strings that were there. All right. Questions? Okay. There's also other output stream functions that we can use, like put and flush. So flush will flush your buffer. Put, I can't remember off the top of my head. I'll have to look that up. Probably you can write to a specific spot in your file. There's a bunch of error state flags. So when we called like cin.good, we could check to make sure that the input was good, no errors. There's also a fail bit for a formatting error. So we can ask to see if the format failed. There's a bad bit for an unrecoverable error. So if this bit is flipped, that means something went really wrong. Maybe our file closed beforehand or something. Input output streams also have this end of file bit, so we can check that as well. And then we can clear all of our bits. I think there's actually, that may not be as easy as it looks, but it certainly can be done. I think you have to specify which bits you want to clear. So you would have to supply some arguments that are basically some constants that they define. So this namespace has a bunch of constants that you can use as arguments. So clear might be not quite as simple as this, but it's not too complicated. All right. So that's it for files. Any questions? All right, so we have 15 minutes left to do a quick review of our exam, I guess. So I didn't actually type anything up. I just put a bunch of titles here and we will talk about, see, these are the categories that are going to appear on your exam. And I'll talk a little bit about the things that you might see inside these categories. So we will start with memory management. Of course, you're expected to know everything else, like you're expected to know programming conventions, basically all of the chapters that came before memory management, but I'm not going to be going over them explicitly. Those are sort of integrated into all the questions anyway. But for memory management, we want, of course, what's the difference between statically and dynamically allocated objects? What are the 4 types of arrays? How do I declare and use them? Right, so we have, we can allocate an array statically, so on the stack or with our object, or we can allocate it dynamically. And then my array can be of statically allocated objects, or it can be of pointers. So then that would imply, I could store dynamically allocated objects or basically objects from anywhere. So yeah, know how to use the arrays. Know what happens in your vector class, right? So if I have a vector of objects or a vector of object pointers, what's the difference? That sort of thing. So yeah, memory management. Object-oriented design. This would be things like the principle of least privilege. What is that? How do we use it? Why do we use it? Also UML diagrams. So you should know how to, make a UML diagram that indicates composition or inheritance, things like that. Yeah, I guess that's good enough. Object design categories. So there's 4 of them. They're the entity, collection, control, and view. So what are these? And what are they used for, right? So entity is basically almost like a data class. So it's low level, doesn't control anything, just store some information about an object. Collection class would be, I would store a bunch of different items of the same type. Control determines the flow, the flow of my program. View objects would interact. Sorry, is this view or boundary? I think that's boundary. Interact with users. Other programs. All right, so if I gave you a object, you should be able to basically choose a category for it within reason, right? I'm not going to try and trick you, but something obvious you should be able to put in one of these categories. Encapsulation, const functions. const parameters, things like that. When is it appropriate to use these? And when is it not appropriate? It seems like for some reason, how to implement a deep copy fell under this category. I may rearrange it at some point, but. So what is a deep copy and when would you need it? Can I ask why you shouldn't make everything static? You can, I mean, that's a different type of programming though, right? That's like procedural, I get. Not, is it, yeah. Procedural or imperative, which are sort of the same thing. The problem is that with making everything static is now I cannot have different instances of the same object, right? So everything in my class is going to be, each class will have only one instance if everything is static. So I do want to be able to make copies of, I want to have different students, not just one single student. Yeah, if I made everything static, even especially the member variables, right? That means I have one instance for my entire class. So yeah, that would be a bad idea. Now I can only have one possible student. All right. Other questions? All right. Inheritance, no access modifiers, and how they affect the derived class, right? So if I have a public function, then of course that's inherited publicly. If I have a protected function, then that is inherited as well. But it remains protected, and the same with my member variables. Private, however, does not get inherited. So access modifiers and inheritance, but also protected and private inheritance. Of course, this affects how you can access things as well, especially when you get down into the later levels. Virtual inheritance, or say multiple inheritance. Right, so I can inherit from more than one superclass. This also brings up virtual inheritance. So you need that if you have the diamond hierarchy. Right, so I have my base class with two derived classes, and then I have this class which inherits from both of them. If I want to have only a single copy of my base class, then I need to inherit virtually here. Yeah. Also, with multiple inheritance, how do I call my constructors? What are the rules? Right, so I'm not going to go over in detail, but you should definitely look that stuff up. And yeah, what is this diamond hierarchy and multiple inheritance mean for the member variables as well? Right, so I'll get, if I don't use virtual inheritance, I get two copies of this base class, and so I get two copies of all of the member variables as well. Design patterns, so there's behavioral, structural, creational, but we'll look at, we'll keep it simple. Observer, which is essentially, I have a list of things and I'm going to call update on them, essentially. Maybe not update, but some function that's saying, hey, something happened, I'm notifying you. Strategy, if I want to swap out algorithms, for instance. Facade, which I'm going to take some complicated procedure and I'm going to hide it using a simple interface, essentially. Polymorphism, virtual functions versus non-virtual functions. And, so what happens if I have a non-virtual function and I call that function using a base class handle, such as animal? What is the change if I use a virtual or a non-virtual function? Operator overloading, cascading. How do I implement cascading? When should I return by reference or by value? Right. So the rule of thumb is I want it to behave like ints. So if I say 2 plus 2, this should return 4, but I don't need to, if I had two variables here, let's say, I don't want either of them modified. So in this case, I would return by value. But if I'm, overloading my assignment operator, then I'm probably going to return by reference. How do I differentiate between the postfix and prefix, increment and decrement operators? Which operators should be global functions? And why, I guess. Templates. So yeah, templated functions, overloaded templated functions. What are some of the consequences of a templated class? Of course, each new type that I use in my template, if I say string, and then I declare another one with ints. Well, these are two different classes. So what are the implications of that? STL, so the iterators is pretty important. Simplest versions of that. We did some complicated stuff I'll probably stay away from, but you should know basic iterator things. Random access, bidirectional, input, output. And sort of when and how you would use them. And of course, exceptions, which we just did. These make good questions because, what happens if I have multiple catch blocks? What gets caught first? What might give me a compiler warning? Yeah, these are really great for code tracing, right? So if I say, well, what happens if this exception gets thrown? What is my output now, right? Because it can be vastly different depending on how that's implemented. So I do like questions on exceptions because you have to understand how exceptions work, but you also have to understand how the code is working below it. So, and yeah, that's it. So the files, I wanted to give you a look at them because it's pretty cool how you can read and write using C in, C out, or not C in, C out, but the input and output streams. But they won't be on the final because, well, basically because the C section did not have enough time to get to them. So everything from memory management to exceptions, and then anything before is fair game, but this is where most of the stuff will be focused. All right, questions? All right, the whole thing took longer than I thought, but that's it for the semester, I guess. So the final exam, I will be on Zoom during the final exam, so you can come on and ask me questions. You can also send me emails. That's fine. Try and stay off Discord during the exam. All right, that's of course, it's open book. You can use your IDE, you can use whatever, but it's going to be, the exam is long and it's by design. So I would not type in every question. I would answer the questions that you find easy and then come back to the questions that you find difficult later and maybe type them into your IDE, see if you can get them running, see, that sort of thing. But yeah, is there anything, other questions? I can't, If you have any other questions, you can also email me. I have my office hours tomorrow, but that'll be it for the semester. But yeah, thanks a lot for tuning in and listening and asking smart questions. It's been a real pleasure. So thank you and best of luck. It's all multiple choice. Yeah. So there's a lot of questions that have a piece of code. So you guys have seen, I'm sure, the practice final. So you'll see a lot of stuff that looks like this without the funny looking lines running through it. And then I'll ask you questions like, yeah, well, here it says, how would I implement a copy constructor for this? Right. So I'll give you a bunch of options and you choose the correct one. Or I might say, leave out a piece of code and then say, well, what could go in here without causing an error? Right. So maybe I'm looking at the access variables, access modifiers for my variables and things like that. So, and what it is usually there's a group of questions. So there'll be 4 questions with these 2 classes, but there'll be slight differences between them, right? So if I'm asking about access modifiers, then I'll be changing the private to protected and saying, okay, what now? Protected to public, et cetera, et cetera. All right. Other questions?